Yeah, so currently Nishant is leading the outreach effort. I did it for quite some time, but I have moved into astronomy education nowadays. So dealing with school students, trying to understand how to get astronomy, how to use astronomy in order to attract them to basic sciences, which is also another passion of mine. Okay, so today we'll talk about cosmology with gravitational waves in this week. But what I wanted to do is to start off with the basics of cosmology, so that we are all on the same page, and then slowly ramp, but very quickly to gravitational waves and how currently the LIGO-Virgo-Kagra collaboration, for example, are using gravitational waves in order to get cosmological constraints. And during the tutorials, you will have today, for example, some exercises about the basics of cosmology. But then from tomorrow onwards, you will start to use some of the tools that are being used by the LVK collaboration, so that you will understand how to use these tools, how to make use of some of the public data that is there, in order to get cosmological constraints, or even to reproduce some of the results. One great thing about all of this is then it will bring you to cutting edge research. And then if there are different kinds of models that you want to try or do some kind of tweaks to the assumptions that have been made in the papers, then my hope is by the end of this course, by going through these tutorials, etc., that you will feel empowered to go to these codes and make some of these changes. Okay, so I hope that you take it in this spirit, and then let's see how it goes. Okay. Okay, so let's get started then. So this is the course plan. So today, and hopefully today and by tomorrow, we'll cover the basics of cosmology. I'll in principle also talk about something called the Hubble tension. So this is a new problem that has been arising in cosmology. And so we'll try to walk you through some of the details of this. Then we will learn about gravitational waves as standard sirens, why people use gravitational waves, why they think it would be, it can give you cosmological constraints. And then we'll try to understand the mapping of the expansion history of the universe through the use of gravitational waves. In particular, I will talk about something called bright sirens, where see gravitational wave events, but then you can also find out an electromagnetic counterpart related to this event. And so that helps a lot in trying to utilize the power of gravitational waves in order to do cosmology. But then, as you all know, you may know, there are not many events for which an electromagnetic counterpart has been detected. And so for the vast majority of these gravitational wave events, they still are able to help you to constrain cosmology. So how to do that? That's the dark sirens part. And then finally, we'll, as time, if time is left around, then we'll also talk about how to utilize the large-scale clustering that is present in the universe in order to use these gravitational waves again. Okay, so this is the rough plan. And so the tutorials are meant to complement this plan. I will be present during the tutorials as well. So in case you have questions or things that are not working, etc., then please let me know. Okay. Okay. So let's get started with some of the big questions that cosmologists usually would like to understand. This field has been going on for ages. Okay, so it's not just like a modern field. People have been thinking about cosmology for a long time, but slightly different questions, right? So initially, when we started in cosmology, we would like to understand, for example, how old is mankind, right? And then what are we ourselves made up of? How did we come into existence? And finally, what is the fate of human beings in general, right? What is going to happen to mankind? So these are kind of the questions that were at the back of many people's minds from like centuries and centuries. So these are age-old questions, and often these used to be in the domain of religion, right? So if you'll find many religious texts which will have some or the other verses which are trying to talk about these kind of questions. Of course, now our field of view has increased, so we have basically expanded some of these questions. So instead of trying to learn just about mankind and about us, what we would like to know is about the entire universe. So we can reframe these questions. We would like to understand, for example, how old is the universe? Right? What is it made up of? What are the components of this universe? How did the universe come into existence? And hopefully you'll learn about the very early universe in the set of lectures which will be delivered in the afternoons during this week. And then finally also, what is the fate of the universe? Is the universe just going to continue as it is? Is it going to expand at an ever accelerating rate? Whether it will have a cold death? And all these kind of questions are things which are very near and dear these days to cosmologists. Okay? The good thing is now these can be actually addressed scientifically. So we've made a lot of progress. For a long time, there used to be a lot of speculation in cosmology. But now with observations being present and with the kind of precision that we can make some of these observations, we can actually try to address many of these things scientifically. Okay, so that's in a nutshell where cosmology is. So let's start at the beginning. I mean, you wake up every morning and you see the sun rise in the east and then set in the west. You can see stars in the evening as well, rise in the east and then set somewhere in the westward direction. And so it is easy to think that maybe we are right at the center of the universe, right? Because everything is rotating around us. It took quite some time to understand that the Earth is not really at the center of the universe. And it took a lot of effort. I don't know, again, because I work with astronomy education in schools, I try to think about these things rather than tell students that this is how it is. It is better for them to understand where it comes from, right? So I would encourage you to also look out for why people started to think that Earth is not really at the center. Because it's very counterintuitive, right? Every day you see the same thing happening, everything rotating about yourself. So it was very common to believe that the Earth was at the center. But various kinds of observations help us to understand that that's not really the case. Okay, so most of the motion that you see is because of the rotation of the Earth, and it took some time to figure that out. And we'll talk over during coffee or lunch about some of these things, how they came about. Okay, but if you look at the solar system nowadays, there are various kinds of methods with which you can measure the distances within the solar system. And so if you look at the solar system, the sun is really the most dominant component of the solar system. Everything is going around the sun, nearly circular, a little bit elliptical orbits. And we can see the various planets that we have discovered together with some of the dwarf planets, which are also listed here. So if you look at the solar system itself, then the light travel time is of about a few hours to a day within this kind of a system. Okay? We can move on a little bit further, like maybe you may think that the Earth is not at the center, maybe our sun is at the center. So you start to look around in the solar neighborhood and you start to see many different stars. Nowadays, you can even get distances to these stars, so you can put them on a 3D map. And you start to look at this, and again, right now it looks as if the sun is at the center. That's just because we are observing from there. But in reality, if you look at it, everything looks quite random, right? Fairly well distributed, many different stars of different types. The light travel time to these is about a few years. Okay, so the closest one is about 4 years or so from the sun. And so, sorry, light takes 4 years to go there. So it's about 4 light years away. But it doesn't seem as if the sun is necessarily at the center. And this becomes clearer and clearer once you start to draw a picture of the Milky Way and try to place our own sun within the Milky Way itself, right? And so if you look at the location of the sun within the Milky Way, you can see that it is not even close to the center of the Milky Way itself, leave alone the universe, right? And so we are in The outskirts of the Milky Way, the central regions are here. In fact, it may be good that we are not in the central regions. There's a lot of high density of stars, lots of light, lots of different radiation. Could be harmful to life even, right? And so we are sitting somewhere near here. But the Milky Way size is also astounding. It's really large. And it is very hard to get a sense of it, and so um, the idea that you should think about is, again, with a light travel time, it takes about 30,000 years to come from the center, for light to come from the center of the galaxy towards us. 30,000 years, right? And again, this may sound like a small number. Think about where we were 30,000 years ago, right? We are just like 2025 after, AD, right? 30,000 years ago, you can imagine what was going on, right? And so light that we see today was emitted at that point of time from the center of the Milky Way. So it takes a lot of time. It just shows how humongous these structures are. So we keep on going. Maybe our galaxy is at the center of the universe, but that also doesn't seem to be the case. So this is the Milky Way here. There's another galaxy nearby called Andromeda Galaxy. There are many, many smaller galaxies which are around. Okay? So it doesn't, again, look like as if we are necessarily at the center. So this idea that we are somehow special gets dealt blow after blow after blow as we continue to make more and more observations, try to map out what the universe is looking like at larger and larger scales. So this galactic neighborhood, now the light travel times are of millions of years, right? And so it takes longer and longer time. So we are looking a little bit further out. This is just the neighborhood of our galaxy, and it's still taking like millions of years. But then you can go even further, map out the galaxies in the nearby universe. You can try to measure how far they are by using something like the redshift of these galaxies and trying to infer a distance based on the cosmological model. We'll try to understand how this is done exactly. But I wanted to give you a glimpse of what this looks like. I hope this thing will run. Let's see. Oh, yes, it does. So this is from something called the Sloan Digital Sky Survey. So what they've done is they've taken spectra of millions of galaxies. And each of these galaxies, because you can get a redshift, you know exactly the position on the sky. You can put it in a 3D map. Okay? And you look at this 3D map and you go like, okay, what is this? This looks like all sorts of galaxies thrown randomly around. There is some sort of clustering. Once in a while, you will find galaxies which are clumped together. But other than that, it's basically a mess. Right? And so what cosmologists try to do is try to take these kind of observations and learn things about the universe. And so how do they do that, etc.? That's going to be the next, today's lecture. Hopefully, maybe a little bit tomorrow. We'll continue into this. But this is what we are getting into. Right? So this is the observable universe. Distances, light takes about billions of years now to travel some of these distances. Okay, let's see. So that brings us to something called a cosmological principle. Okay? And this, again, you may have heard about this if you have done some introductory lectures on cosmology. What does the cosmological principle states? The cosmological principle states that we are not special in the universe. Neither is our location special. Neither are any directions that you see. None of them are special. So it can be quantified in two different ways. One is called homogeneity, and the other one is isotropy. Homogeneity is something related to invariance under translations. Okay, so if you go from one place to another, the statistical properties of the universe don't change. Okay? And so, of course, the universe is not exactly homogeneous, right? If I look towards this direction, I can see you. I don't see you in the same direction. So on very small scales, you will see inhomogeneities. It's the same thing. If I look towards one planet, I don't see the same planet in all different directions. So it's not exactly homogeneous. But on large scales, if you average on large enough scales, you'll start to see homogeneity. Okay? Then the other one is isotropy, which is in different directions. If you see that the universe looks the same. And at first glance, you would think that homogeneity may also imply isotropy, but that's not really the case. Okay, and so we can go through some examples. For example, you can see a cylinder here. You take it to be infinitely long, then it is homogeneous. The surface of this cylinder is homogeneous because whichever point you go to is exactly the same. But if you look at directions, then it's not really the case, right? Because in some directions are special, you walk along those directions, you will come back to the same point. So you can go around the surface of a cylinder, you can come back to the same point. But if you walk along the axis, then you will just keep on continuing to walk, right? And so isotropy is broken, but not homogeneity in this case. Similarly, if you look at the surface of a cone, and if you stand right at the apex of the cone, you will see that each of the direction along these surfaces looks the same. But this is not really homogeneous, because if you just go towards another location on the surface of this cone, you'll start to see that the homogeneity assumption gets broken down. Right? And so these two principles, both of them are important. It's not just one or the other. And then, so we have realized that the universe is homogeneous and isotropic on the largest of scales. And these principles are also something that can be tested with observation. So what are the observational evidences for this? So for homogeneity, what you can do is you can carry out these big surveys of galaxies in the sky. And what you can do is you can divide the universe into big chunks, okay, of volumes, say big boxes. And then you can ask, okay, how many galaxies do I see in this part? How many galaxies do I see in that part? How many galaxies do I see in this part? And so you can keep on mapping this out. And what you'll realize is that there are tiny fluctuations in the number of these galaxies that you can see in a large enough volume. But as you increase the scale on which you are averaging out, so as you increase the scale of the boxes in which you are averaging, you'll start to see that this variance is actually falling down quite quickly. Okay? And so the variance in matter over densities, as you smooth on larger and larger scales, it starts to fall down. So that's the evidence for homogeneity, and people have to try to establish what is exactly the scale on which the universe becomes homogeneous and so on, okay, by using these large surveys like the Sloan Digital Sky Survey that I showed you before. Then we come to isotropy. So invariance under rotations, the best example for this is the cosmic microwave background. So you look in whichever directions, it looks roughly the same. Okay? In fact, when the cosmic microwave background was initially detected, people were very confused because it was looking exactly the same in all different directions. And if that is the case in the very early universe, if everything was just homogeneous, then how come we are here, right? Because we are part of the inhomogeneities that we see in the universe. And so what led to inhomogeneities like us was a big question. So there was a big race for the discovery of these inhomogeneities, which culminated in the 1990s and when we first saw the inhomogeneities in the cosmic microwave background. But the point to convey is that these inhomogeneities are extremely tiny. Okay? And so the universe is really isotropic on these larger scales as well. But we do see some time asymmetry. So light allows us to do some kind of a time travel, right? As I said, it takes finite amount of time for light to arrive towards us. And so the longer or the farther some of these galaxies are, we see them when they were a little bit younger. And so there is a time asymmetry that you can discover through this by studying galaxies in a region of sky by going like further and further depth. So fainter and fainter galaxies which are further and further away. You start to see that the structures in these galaxies are slightly different. So if you look at galaxies nearby, you see these well-formed arms, big elliptical galaxies. As you go earlier and earlier in the universe, you start to see clumpy star-forming galaxies. Okay? So there is a time asymmetry that is involved in the universe. So this is how we can actually start to describe what the universe is looking like by looking at the observational evidence and trying to build models for the universe based on. So let's start to build some of these models. In these models, we can start with something called fundamental observers, okay, where you can set up a grid, okay, like this, the one that you see here. And what you can say is that if you take this grid, and let's suppose that the universe is completely homogeneous and uniform, so things are just sitting on these grids, which is not exactly the case, just randomly distributed around this. Okay? I can maintain the homogeneity and isotropy even if I keep on scaling this grid by an arbitrary amount. Right? At any point of time, even if I take this grid, I scale it by something, something else, it will still maintain homogeneity and isotropy if I start from homogeneity and isotropy. Right? So this allows us to build a framework for a homogeneous and isotropic model. Right? So you have some fundamental observers. We will say that they are sitting on some kind of a grid which we can define at a particular time. Let's call that time today. It does not matter whether you define it at initial point or later point. Okay? And then if you want to measure distances, you can measure distances directly on this initial grid, and those are called moving distances. But we will allow these distances to change with some kind of a factor. So this factor is shown as A of t here. So the physical distances will be given by some scale factor times the moving distances. And if this is the case, then if homogeneity and isotropy is there in the beginning, it will stay all throughout. Okay. Is that okay? Yeah, so now we can think about galaxies maybe sitting on some of these grid points, not everywhere, not necessarily exactly at the grid points. Grid points are just for our convenience. They are just like a graph sheet that we have so that we can measure distances, right? But then after that, the physical distances, all the physical laws that you see, they will be governed by this physical distance. And we maintain homogeneity and isotropy. So this allows us to build models for the universe. Now you can say, what about time axis? We don't know actually in what direction time will go. Does the scale factor keep on increasing or decreasing? Homogeneity and isotropy will not tell you that. It could be either. It could even be fluctuating up and down. What we have to do is carry out observations in order to figure out what is indeed the case. Just with the cosmological principle, you cannot tell. Okay, so in terms of general relativity, you can come up with the metric of space-time. Okay, that is the most fundamental concept in GR. And so this metric, you can write it down as ds square is g mu nu dx mu dx nu. This is the most common way of writing the metric. The metric tensor g mu nu here is what will tell you what space-time is doing. And so let's talk about this metric tensor in homogeneous and isotropic spaces. Right? So what you can do is you can set the time to the proper time of fundamental observers. And so if you do that, then this G00 component will become minus C square, because for the fundamental observers, they are not moving at all. So all the spatial components, dx's, are all zero. So that is just dt square, right? So ds square will be minus c square dt square in that case, right? And so if you set the time to proper time of these fundamental observers, then this G00 component should be minus c square. But then we have said that we want universes which are isotropic, and so there are no no favored directions. And so that's why if you look at the dxi dt kind of components, so it is 0i components, then they have to be 0. And so that simplifies the metric to look something like this. ds square, the minus c square dt square is this G00 component. Plus, you can have some kind of a scale factor, as I said before, and then a length element that describes the lengths within the three-dimensional space that is left. Right? And the space component here, this dl square, has to be homogeneous and isotropic. Okay, if that is the case, then we can have a metric which obeys both homogeneity and isotropy, and it will allow us to write down models for the universe. Is this clear, maybe, or was it too fast? Okay, just let me know if it is too slow or too fast either. Okay. Okay, so let's move ahead. Try to understand what this DL square part could be. Okay, so we started with the metric. We said where exactly the scale factor can go. And then we said that now we have to find out homogeneous and isotropic spaces, but in 3 dimensions now. So let's talk about such kind of homogeneous and isotropic surfaces. They are called maximally symmetric surfaces in geometry. And so it turns out that it's easiest if you think about things in 2 dimensions first, rather than going to 3 dimensions. Okay, so let's start with 2 dimensions. The simplest thing that you can think about in 2 dimensions, which is homogeneous and isotropic, is an infinite plane. Right? So a plane which extends out to infinity. There are no borders or edges, unlike the ones that's shown here. So you can imagine this extending out to infinity. You can write down what is the distance metric. So if there are 2 points here and here, again, imagine a grid being set up on this plane, right? Rectangular grid. And then you want to measure the distances between any 2 different objects which lie on this plane. And this is just given by the normal expression that you know of, that you're very well familiar with. dl square is equal to dx square plus dy square. No problem here, right? Now, you can also imagine other homogeneous and isotropic surfaces which are not exactly like this infinite plane. Can you think about them? Do you have any suggestions for such surfaces? A sphere, right? So if you can take a sphere and the surface of a spherical object, then that object, at least in 2 dimensions, you can see that it is homogeneous and isotropic. Because wherever you go, does not matter. It gives you exactly, it is exactly the same thing, unless it's rotating or something like the Earth. Then you start to see differences. But otherwise, other than that, it should be exactly the same. So it is homogeneous. And it's also isotropic because whichever direction you go, it's exactly the same, or you look at, right? So then let's try to think about the surface of the sphere. Can we write down the metric for the surface of the sphere? So eventually what we want to do is to try to find an expression for this dl square, okay, in the metric that we have. Okay, so let's think about dl square on the surface of a sphere. So it is easier to imagine these kind of curved surfaces in higher dimensions rather than working on it directly using coordinates which are set up on the surface of the sphere itself. And we'll see easily, we'll see quickly why that becomes important. So then, if you consider this surface as an embedded thing within 3 dimensions, a curved surface embedded in 3 dimensions, then the dl square, you can still write down the normal expression that you're used to, dx square plus dy square plus dz square. But now you say that because you want to just lie on the surface, you want to only explore the surface, then you are constrained such that your x and y and z are not going to be completely arbitrary. Okay? So if you set a constraint that your r square should be equal to x square plus y square plus z square, then you are sure that you will always lie on the surface of this sphere. And if you do that, if you use this constraint equation and try to also satisfy this, you will see that you can do that if you write down your dl square as this. Okay, so there is a way to derive this. So let's take this constraint equation, r square is x square plus y square plus z square. I can redefine my coordinates to theta phi coordinates, where my z is equal to r cos theta, and x and y are r sine theta, sine phi, r sine theta, cos phi. If I do that, my constraint equation is automatically satisfied. So this is the kind of spherical transformations that you would be used to in your master's courses in physics, right? So you do that, and then you are automatically going to satisfy this equation. And then you'd start to plug in what is dx, what is dy, what is dz, and you will end up with an expression which looks like this. So the metric of the two-dimensional surface of the sphere of a radius r can be written or can be found out by first starting from the three-dimensional embedding and then working out together based on a constraint equation. So similar to this, what you can do is you can now try to generalize this to 3 dimensions. Okay, so in 3 dimensions, something which looked like the infinite plane, you can generalize it to this, okay, to this kind of a metric, dx square plus dy square plus dz square. But similar to the surface of the sphere that we had, you can also have curved surfaces, positively curved surfaces in 3 dimensions. Okay? And if you want to work out what the metric for this positively curved surface in 3 dimensions is, you again use an embedding in 4 dimensions and then use a constraint equation to make sure that you are lying again on the surface of these 3 dimensions. Okay? Yes. So I'm going to come to that, right? So this is the simpler thing is the dx square plus dy square plus dz square. But then if you want a curved surface, then it comes with a constraint equation. Okay? So it's easier to do this in 4 dimensions, right? If you do like this, so you can start with a Euclidean metric or a non-Euclidean metric, and then that has this minus dw square kind of a term. And you use this kind of constraint equation or that kind of constraint equation, you will be able to find the expressions for what dl square looks like. Okay. Now, look carefully here, because in dx, dy, and dz, you are still homogeneous and isotropic, right? Because you are not favoring any particular direction in any sense, okay? Even by looking at a metric which looks like this, because this dw square is in a dimension that you cannot really perceive. And that gets thrown out because of this constraint equation. Okay, so if you want to satisfy something like this, just like in 3 dimensions, we did the following transformations. So we did something like this, right? Z is equal to r cos theta, and then x and y. Right? So what you can do is you can add an extra coordinate here, w. Okay? And then you can do r cos chi. And then everywhere here you add sine chi, and sine chi. If you do this, you will notice that automatically that the constraint equation will be satisfied. Just because sine square chi plus cos square chi is 1, you start to add all of this, you will start to see that you will obey that constraint equation without a problem. So these are tricks that you play, and then you can differentiate this dw, dz, dy, dx, write it in terms of d theta, d phi, and d chi, and then sum up all these terms by squaring it all up, and then you can get a metric. Right? Similarly, what do you do for the bottom one? Any ideas? You can use hyperbolic functions, right? And so similarly, you use hyperbolic functions. So in the tutorials today, you'll see some exercises which will ask you to do this just to get you started with things, okay? And for those of you who are not fully familiar or have heard about these things, it will be good. Okay, so the expressions that you start to get are these, okay? You can see here that I have written even the flat space expression, instead of writing it like dx square plus dy square plus dz square, I've also done some kind of a transformation here to get it into a familiar form that you may have seen before. So this is a form again coming from spherical coordinates, right? So d chi square plus chi square times d theta square plus sine square theta d phi square. So this is something that you get for flat space. In the case of positively and negatively curved spaces, you start to see that this expression remains the same. So d theta square plus sine square theta d phi square. This is the angular parts. This remains the same. But instead of having a r square here or chi square here, you start to see this kind of sine or sine hyperbolic functions. Okay. So these are the possibilities of these maximally symmetric things which are homogeneous and isotropic. And that tells you what the metric looks like, okay, in these cases. So now we can put it all together to understand what the total metric looks like. We can combine all these things together into a more compact looking expression. And it looks like this. DL square is some a square of t. I told you that you can scale things with time and it does not change the homogeneity and isotropy. And then you put in a d chi square plus some f square chi function, because this was common in all the three metrics you could see here. The only thing which is different are these three functions. And so those I can define as f of chi, and those are shown here. So if you have positive curvature, there is a sine function, negative sine hyperbolic, and flat is just chi. Okay? So yet there is no general relativity being used as such, right? We are only using homogeneity and isotropy, that's it. But just with this kind of a metric, you already can do and learn a number of things. So let's look at them. Yeah. Yeah. Which one? Which R square, sorry? Or the second and third. So sorry. So let's check quickly. So my chi has the same, I mean, ignore this, okay? Here I'm going to define R cos chi by R. Indeed, right. So once you do this, then all of this simplifies, right? Okay. So that was one of the tricky things that I was going to do in the tutorials, but you should, yeah. Right. Okay. So then we can learn, for example, about the what happens to the velocities that you will measure for galaxies, for example. Okay. So the physical distances, as I told you, they look like a of t times the comoving distance. So my comoving distances will be measured on the grid for chi, right? And then the physical distance, which will come out using this dl square, will be a of t times d chi, right? So the same thing I can do. I'm calling this r comoving right now, distance between two galaxies which are sitting on that grid. The physical distance between them will be a of t times r comoving. And if I want to calculate the velocity, I have to take a derivative of this quantity. And so I take a derivative, I use the chain rule. So dA by dt times r comoving plus a of t times dr comoving by dt. And this thing, I can do a dot divided by a and a times r comoving, which is the physical distance, right? So again, I'm going very quickly through this because I suppose you have seen many of these expressions before. But I wanted to make sure that we are on the same page, okay? So the velocity gets these two different components. One is the one with this a dot over a times r physical, the distance between two galaxies, physical distance between two galaxies, and then this other component, which will tell you if galaxies are moving on that co-moving grid. Okay, so if they are not stationary on that grid, then there is going to be some component of velocity which can be attributed to that. Okay? So this component is called a cosmological recession or cosmological velocity component, and this component is called a peculiar velocity component. So as you go further and further away, this component becomes lesser and lesser important compared to this component that you are seeing. So the change in the scale factor itself will give you some velocities for the galaxies. And by looking at these velocities, you can learn something about what is happening to the universe, how the scale factor is changing with time. So if you remember, I told you, you cannot determine just using the principle of the cosmological principle whether a of t should be growing or decreasing, right? And so you need observations for that. There's no other way to do it. And so the first evidences for this came from Edwin Hubble. He was measuring stars in nearby galaxies. He was able to figure out what the distances to these galaxies were. And then he made this plot. So he measured the spectra, he could get the velocities. And so unfortunately, these are written in kilometers, but they're kilometers per second. And then on the x-axis, the distances that he had got from the measurements that he had. Right? And how he did that, again, we'll try to come to that as well. Okay. So you look at these distances, this is 0 here, 10 to the 6 parsecs, so about a megaparsec here, 2 times 10 to the 6 parsecs, 2 megaparsecs here. And velocity is 500 here and 1000 here in case it's hard to read. And so he had a number of measurements and he said that, well, it looks as if it's a straight line. The further away these galaxies are, they are going away from us with a certain velocity. And the higher velocity for larger distances. Yes. We'll come to that. Part of this is peculiar velocities, and then part of it is also the fact that he messed up the Cepheids that he was looking at. And so that's the next thing that I was going to come to. So you look at this graph and you can calculate the slope of this graph, right? Because you can see that he wrote down that the velocity is some constant times the distance, right? So that's exactly what you see here. Velocity is some constant times the distance. And so he wanted to measure this constant, so you take the slope of this line. What is the slope of this line? I told you, right? This is 1000 kilometers per second, 2 megaparsecs. 0, 0 is here. It's about 500 kilometers per second per megaparsec. Right? So that's large, and that's the value that he got, right? Nowadays, we know that this number is close to something like 70 kilometers per second per megaparsec. They still debate about it, but not at this kind of a level. It's about at a 10% level. Dashed line, different kinds of fits that he must have performed by ignoring some of the galaxies and so on and so forth. There are some open points and then the closed points. Now I don't even remember what some of these things are. Okay, but the point is, he was able to observe that at least this part, this A dot, is positive. Okay, and what A dot positive meant is that the universe is continuously expanding. Okay. And this expansion was something which was new. I mean, at that time, when GR was found, Einstein himself was trying to look for static solutions of his equations. And the fact that Hubble observed this then led him to discard all these static solutions. Because naturally in GR, you get things where the A of t is quite dynamic, so it can change. Does not tell you necessarily how it will change, in what direction. But he was trying to think about static models at that time, so that he could abandon after these observations. So it got, it definitely led to a profound change in our understanding of the universe when we looked at these kind of graphs. So then another thing that we will be talking about during this course will be redshifts of galaxies. I already mentioned redshifts when I showed you that map from the Sloan Digital Sky Survey. So let's try to understand redshifts, but in this formalism that we have. Right? So we have a galaxy which is situated here, and it emits some photons towards an observer who is sitting there. Then you start to look at the metric that we had written down. Let's orient our coordinate system such that the galaxy is basically along one of the axes. Okay? And the photon is just right traveling towards us. Okay? We can set ourselves at the origin, for example, and then try to do that. Then all the d phi and d theta, all these terms will be 0. Okay? The only term that remains is d chi. Right? And so, because photons travels on null geodesics, so ds square you can set to 0. And what that will do is give you an expression for c times delta t. It will be related to the physical distance that light is traveling in a small amount of time dt. And that should be equal to a of t times d chi. So some comoving distance that it travels times the scale factor at the time when the photon was at that location. Right? Okay, is this okay? So c dt will be a of t times d chi. So what you can do is you can sum up all these d chi's. Okay, so you take this a of t in the denominator on the left-hand side, and you sum it all up. And you sum it from the time of emission from this galaxy to the time of reception. What that will allow you to do is to find out what this comoving distance between the galaxies is. So you carry out this integral c dt over a of t, it will give you the distance on that grid for you. Okay. Now let's consider light. Light will have some crests and troughs, right? Let's imagine one of these crests that is being emitted at time of emission, TE. In the next crust, it will come at a time TE plus delta TE. Okay? The distance between this, the wavelength of the light that is emitted will be related to the distance between this crest and this crest. So C times delta T is equal to the wavelength of this light. So similar to what we wrote down for this particular crest, it started at T, ended at TR. What you can write down is for this particular crest. Okay, what will it do? Similar to this expression, you can write down another expression. So it gets emitted at T plus delta T, gets received at TR plus delta TR. And then you again carry out this integral. You notice that the right-hand side is exactly the same. So that can drop out. So what you remain with, you can equate this expression to this expression. And what you will notice is a lot of this expression is exactly the same. Okay? It's an integral over time. And a lot of the time is exactly the same. Only at the endpoints, things are differing. Okay? So if you take out the common parts after equating these two left-hand sides, what you are left with is this particular expression. Okay? So try to do this. So this is the time axis. Okay, so I have started at TE, and this is TR. And then there was another one which was emitted at TE plus delta T. And this is TR plus delta TR. Right? I'm saying these two are equal. But this part I can cut out because these are exactly equal. So the only thing that remains is this part and this part. Okay? So that is what this expression is telling you. And so if you look at that, you can now write this down. C times delta TE is equal to the wavelength of light at emission. But C times delta TR will be the wavelength of light at reception, what you will receive, right? Because how will you measure the wavelength of light that you receive? One crest and then another crest. And so depending upon the time of arrival of these crests, you can figure out what the wavelength is. And so C times delta TR will be equal to the wavelength that you see at reception, okay, on Earth. And so you take this function. So this is lambda E by A is equal to lambda R divided by A at the reception, right? So this is at emission and this is at reception. Yes? Evolution of 80 is not assumed to be constant. Okay, assumed to be constant within the time period that one crest and the other crest was. Yeah. So, I mean, light is oscillating quite rapidly, right? And so on those time scales, things are not changing. And that's the reason why. Yeah. Okay. It's actually an integral, right? Yeah. Indeed. Yeah. It's an integral. And so you can write. Yes, exactly. So that's what I'm doing here. But in reality, these are infinitesimally small. Just because the wavelength, I mean, the oscillations happen really quick. Okay. So then you take the expression for lambda R and lambda E. You see that it is related to the scale factor at reception. This is called the scale factor, this A of T, which scales the universe up and down. Right? And then this one is the one at emission. And so the wavelengths are related to the scale factors at reception and at emission. And this kind of a quantity, lambda R by lambda E, this you can write down in terms of something called a redshift as well. So this you define lambda R by lambda E as 1 plus Z. So the redshift will be 0 when the reception wavelength and the emission wavelength is exactly the same. There's no difference whatsoever. And so if we are seeing galaxies all throughout the universe with an average redshift of 0, then you would have said that the universe is not expanding. But instead, what you see is predominantly the redshifts of galaxies that you see, they are greater than 0. And if they are greater than 0, what it means is that the A of TR that you see, the scale factor at reception is larger than the scale factor at emission. which means the universe is basically expanding, right? If that is the case. And that's exactly what Hubble also observed. The rate, okay, so even the rate argument, I think, should give you exactly this. But you are saying, I mean, it is true that the rates of arrivals also change because there is a delta t which is involved, right? And the delta t will also be related to the scale factors in the same manner. So, for example, if you are emitting photons from a certain object at a particular rate, and then it is being received later on in the universe, then even the rates change by exactly the same factors. But I agree that that may not tell you necessarily about the energy change of the photons in that case, right? But the rate also changes. The rate does not remain the same. Yes, indeed. So there is a component. So this one, we are ignoring, for example, all the peculiar velocities, that these things are sitting stationary on the grid. If they are not stationary on the grid, then of course this will not necessarily. So this is at large scales, right? Yeah. So in addition, so redshifts will have a component from both the peculiar velocities as well as this cosmological component, as you can see here. But as you go to larger and larger distances, you start to see that this one becomes smaller. And again, there is an exercise which we will try to ask you at what distances does it become like 1% or something. You can calculate. Okay. Good. So then, so we worked out how to measure some of these coordinate distances. This will require you to know what the scale factor is, but we don't know exactly how the scale factor is changing with time. Okay, so that actually requires you to use equations of general relativity. We'll go there, but if we had an expression for what A of t looks like, then we could have gotten the grid distances. Okay. The distances that you can measure in observations are instead something like this. Okay, so they are called angular distances or luminosity distances, angular diameter distances or luminosity distances. So how do they work? They work on the principle that so let's look at the angular diameter distance first. If I take something like this water bottle here, if I hold it closer or if I hold it further away, the angle that I see between the edges of this bottle, that will change, okay? And that angle can help me tell how far away that object is. Okay? And so you can define this angular diameter distance as the relation between angles or the solid angle of an object and the physical size or the physical area of this object. So this is one way. So the angular diameter distance is the physical area of the object divided by the solid angle that it subtends, and then you take a square root of it. This is again the same as the meter scale. So in 2 dimensions, this is the area. Otherwise, it is the length of an object, and then the angle subtended by the edges of this object. So what is the area then? So one thing that you can do that is if you want to define this angular diameter distance, you can look at the entire sphere. Okay. So if you look at the entirety of the sphere, you can start with the metric expression that we had. Okay, so this one, where did it go? This one. Okay, and you can ask what is the area of the sphere. Okay, so if you want to calculate the area of a sphere at a distance chi, this d chi is 0. All you are left with is f square chi, d theta square, sine square theta, d phi square. So you take this area, you can define an area element based on this, okay, and work out what the area of the sphere is going to be. Right? So there will be an integral over d theta and d phi going from 0 to 2 pi, d theta such that, you will have a sine theta, d theta, which turns into a d cos theta, where cos theta goes from -1 to 1. So you carry that integral out, you get 4 pi. That is basically how you derive that the area of a sphere is 4 pi r square. So in this case also you get 4 pi, but then you have this factor f square of chi and the a square of t. Right? So these two extra factors will be there. So you take that area and then you divide by the solid angle which is subtended. That solid angle will be 4 pi. So you see this 4 pi times f square chi times a square of t divided by 4 pi. These 4 pi's cancel out, you take a square root, you get an expression which looks like this. Okay. So it's some function of this co-moving grid distance divided by 1 plus z. That's what you get. It's not exactly equal to the coordinate grid distance that you would have found. Okay. So that's one. The other thing that you can do is to define the distances using the relation between the luminosity of an object, so the energy per unit time that an object emits, and compare it to the flux that you see. And the flux that you see can be measured as the energy per unit area per unit time that you receive at a particular location. Okay. So you can go through the derivation for this, and this you will see in the exercises in the lecture notes that I have prepared, that you will be able to see this full derivation. It turns out, it comes out, it comes out to be something like this, f of chi times 1 plus z. Because there are two things again that go into this. One is the energy that is emitted compared to the energy of the photons that you receive. There is a factor of 1 plus z, as we saw before. Right? And then the timing argument that he was talking about, per unit time in the source frame is different from per unit time when we observe on the Earth. Okay? Plus the area or the sphere of the surface on which all these photons are going, that also contributes. Okay, so all of this, when you put it together, then it gives you f of chi times 1 plus z. You can see that these two are not the same. The angular diameter distance is a 1 plus z in the denominator. This one has a 1 plus z in the multiplicative factor. So if you measure distances in these two different ways, you will get two different answers. Okay? It's not that either of them are right or wrong. Both of them are okay as measures of the distance. And you have to use these observations in order to learn about the universe. So how do you do that? So in order to use these objects, so let's talk about the luminosity distance first. What people have done is they have established something called a cosmic distance ladder, because it's not easy to find out objects which have exactly the same luminosity. Okay? Or even if you find out objects which have the same luminosity, it's very difficult to know what is that luminosity in reality. Okay? So you need to calibrate these luminosities. What exactly is the standard luminosity that your object has? Okay? So in order to do that, people have done these kind of methods. So again, I will not walk you through all of this. The radius of the Earth, for example, this is the most basic thing that you can start off. And historically, there were measurements based on simple stick shadows. And these are experiments that even school students can do. Okay, so these are things that you should look up, how the radius of the Earth was measured. Once the radius of the Earth was measured, then you can measure the distance to the moon by timing the eclipse that happens, the lunar eclipse that happens. So you get the distance to the moon based on the radius of the Earth, okay, by doing these experiments. Then you can get the distance to the sun. So this is what is called the astronomical unit. In order to do this, you can use a very age-old method, which is you try to find out exactly when the moon shows half phase. Okay, where only half of its side, half of the surface of the moon is bright. If you can observe that and try to measure the angle with respect to the sun, okay, so the angle between the sun, Earth, and moon when the moon is at half phase. And in the olden times, people tried to do that. They could not do it accurately, so they got distances wrong and whatnot. But this is a very cool geometric method. Again, something that you should think about, why it works, how it works, etc. So you do this and you can get the distance to the sun. So even quite early on, this distance to the sun was a quantity which was very difficult to measure. So even after Kepler found out his laws that orbits are elliptical, the t square is proportional to a cube, people had not established what exactly the scale of the solar system was. And in order to do that, there were people who were trying to look for the transit of Venus in front of the sun. So if you look at the sun, there are times when Venus just passes on top of the disk of the sun. And this can be used to measure the distance to the sun. In fact, this was the first way that we got somewhat of a accurate measurement of the astronomical unit itself. So this happened later. So you can think about even the genius of Kepler, right? That he could figure out all these laws without actually knowing the exact distance between the Earth and the sun. But nowadays, there are radar measurements that you can do to different planets, which helps establish these distances much more accurately. And so you can get the astronomical unit. And then once you have the astronomical unit, then you can use something called parallaxes. Okay. So if I use my finger here, and if I close one of my eyes, then I see that this finger is towards you. But if I close this eye, then I see somewhere towards the other side. So as the Earth moves in the orbit of the sun from one location to the other, the stars which are nearby, they start to move around. Okay, so you start to see them at different locations. If you can measure these different locations, then you can figure out what the distance to this star is. Okay? Further away objects that are there, they don't seem to move. And so you see this motion in the background of really distant stars. So you try to do this, then you get the geometric measurements of these parallax in terms of the distance between the sun and the Earth. Okay? So there is a distance ladder that you have to establish, which means every time you measure these distances, you're doing it as ratios. Okay? So initially, Earth to the moon, then moon to the sun, then sun to the nearby stars. And then from nearby stars, you try to go further and further. So this is typically nowadays done. So this is, once you come to distance to the sun, you have the geometric parallax method for nearby stars. And then you try to go even further upside, you can do it using masers. So there are these nice objects which emit lines at a very specific wavelength. Okay, so these are clouds which are near some active galactic nuclei, and they are masing. Okay, so just like you have lasers, these are masers, and then they emit light at a particular wavelength. You can measure this light that is coming in radio. And when you do that, you can measure the velocities of the clouds that are going around. In addition, you can use the VLBI technique, so very large baseline interferometry technique, to also figure out what is the acceleration that is happening. Because these clouds move, and the movement of these clouds you can trace out. And so you can even figure out what is the acceleration of these clouds. So you put it all together, you can again get a geometric distance. Okay? So you use each of these things to climb up the ladder. And then finally, why do you do this? Is because you take this galaxy, if you have certain stars or say supernovae, which have occurred in this particular galaxy, you have a distance measurement to that galaxy, you have a flux measurement of the supernova or flux measurement of some of these stars, and then you can establish what is the absolute luminosity of these objects. Okay? So that's how you calibrate things. Okay? So in order to do that, we owe a lot of things to this particular lady, Henrietta Leavitt. She found a period luminosity relation for something called Cepheid variables. These were the stars that Hubble used in order to get the Hubble constant or the measurements of the expansion of the universe previously. So these stars, you can see that their magnitudes change as a function of time. So magnitudes are astronomers' ways of measuring the brightness of objects. So they are going up and down. And what she found out is that there is a relation between the periods of these objects and the luminosities that they have. Okay? And so if you can measure the period of a Cepheid, you can tell what is the absolute luminosity of this Cepheid. You measure its flux, and you can tell the distance to this object. Okay? Do you see the connection, right? You take the period, and you can figure out what the absolute luminosity of this object is, and you measure the flux as seen from the Earth, then you can get the distance. Yeah, so this is phase. So what they typically do is that they monitor this for a long, long period of time. Then they see that there is a periodicity, and then they fold the light curves. So that's the reason why this is called a phase. And so when you fold it, then you can see Yeah, so it may not be well sampled like this during one kind of oscillation that happens. So these Cepheid variables are typically days. Okay? And then there are certain things like RR Lyrays, etc. They can vary on hours kind of time scales. So in this case, I think these were bolometric measurements at that point of time. But yeah, you can have these in different bands and then they also play a role.
Do we understand why there is a correlation between this absolute luminosity and the period of these objects?
So, I mean, I think for Cepheids, it is a little bit better known than for other objects. The mechanism for these oscillations is very well understood. But I think there are people who are still working on. I don't know the exact details of what this mechanism is, which gives rise to this period luminosity relation. But presumably, it has to do with the fact that if your star is larger, then the time scale of this oscillation should also be larger. And so then that's what causes, I mean, to zeroth order, basically. But I think you'll have to go through papers to like years? What is the month? No, this is, Cepheids are like in days times. Yeah. So these are quite rapid. Yeah. Okay. But then there are different types of Cepheids as well. There are Cepheids of type 1, type 2, and all of them, there's a mess, basically, a zoo of this. And the reason why Hubble got this constant to be really large is because he was confusing these different types of Cepheids that he had observed. But nowadays, we can do this to larger and larger distances. So this is a compilation from ReSita. You can see the geometric measurements are here. So these are based on parallaxes or the masers. I think one of these amazing galaxies is here, NGC 4254. Yeah. And so what you can do is you can take the Cepheids and show what the apparent magnitude minus the absolute magnitude is. And you can try to get the absolute magnitude of Cepheids by saying that these should lie on a straight line. The distances that you get from geometry should be the same as the distances that you get from Cepheids. Okay? So you observe the flux of the Cepheids and you say that my absolute magnitude for the Cepheids should be such that this gives me a straight line in this axis versus this axis. What geometric? Geometric means either geometric parallaxes or via this kind of maser distances. So this one is maser, okay, then M31, LMC, and then there are many, many things in the Milky Way. So you can get the absolute magnitude of Cepheids based on this relation. Okay. Now Cepheids are these big and bright stars, and then that's why they are in this instability strip and they're oscillating. Now what you can do is you can look for galaxies which have Cepheids, but in the same galaxies there have type 1a supernovae which have occurred. Okay? So type 1a supernovae are also standard candles, but we don't know exactly what is the absolute luminosity of these candles. And so you again try to calibrate them, but now using the Cepheids that you have calibrated to the geometric measurements. Okay? So you play the same game, you use the absolute magnitude from here, you say that as I go further and further out, the absolute magnitudes of the Cepheids is not changing. So now I can plot the x-axis here and then try to figure out what is the supernovae 1a absolute magnitude by ensuring that this axis versus this axis gives me a straight line. Okay? And once you do that, then you can take the absolute magnitude of this supernovae on this axis and then plot all the supernovae that you see out to even further distance. Because Cepheids are single stars. Supernovae are also single stars, but completely exploding. And it's a thermonuclear explosion that happens in supernovae 1a. So now you can see those to even larger distances. So now you can calibrate out one by one and try to figure out, measure these luminosity distances of objects as a function of the redshifts of the galaxies in which they are occurring. So that is this particular relation that you see. So using all these measurements, there are the SHOES collaboration, for example. Adam Rees has been leading this effort in the last few decades, I would say, decade or so, I would say. And then they get basically percent level, sub-percent level accuracy, or percent level accuracy on the measurement of the Hubble constant. Okay? So this is 73 plus minus 1 kilometers per second per megaparsec. No, so you have to fit exactly what the luminosity distance is that you measure from supernovae as a function of the redshift. That is not here shown. It is in the model here. Okay. So it's not exactly this, the slope of this. Yeah. So how even Hubble even got this? No, so you can see here, first of all, I'm not measuring. There is nowhere a redshift here. This is just distance versus distance to do the calibration. See, in the nearby universe, you need geometric measurements because there are so many peculiar velocities. You cannot use velocity redshift relations there. So in the nearby universe, you use geometric measurements to figure out what are the absolute magnitudes of things. And then you use those absolute magnitudes to go further out, okay, where you can reliably measure without having to worry about peculiar velocities. So that's the idea. You calibrate in the lower redshift regime, and then you go further out and you measure the distance versus redshift in the faraway universe. And it does not look necessarily a straight line. It will have changes. In fact, in the tutorial, if you do the tutorial today, you will write a code to calculate the luminosity distance as a function of redshift, angular diameter distance, and see how it behaves. Okay. Okay, so I'm going too slow, maybe. What's the time? Oh, 5 minutes. Okay. So now let's come to the scale factor itself as a function of time, because that is what is important in order to figure out what this distance versus redshift relation should look like. So you start from the Einstein's field equations. G mu nu is 8 pi gt mu nu by c to the 4. And you ask for a homogeneous and isotropic universe what this T mu nu should be. Okay, so the energy momentum tensor, you can write it down for something called an ideal fluid. And this looks something like this. It has the energy density and the pressure of the components of the universe that are present. Okay, yeah. And so you solve this equations in order to understand what the scale factor of the universe, how does it depend upon the constituents of the universe. Okay. So this seems like a daunting task because there are too many variables, too many equations, etc., that you have to do. But again, in the tutorials, you'll see I've set up a Python notebook, which allows you to use a Python package called Einstein Pi. You can see how to define a metric that we had defined for a closed universe, open universe, flat universe, and so on and so forth. And then to solve these equations, to figure out what are the what do these Einstein equations tell you if you were in a metric that we had defined for homogeneous and isotropic space. So it turns out that it gives you these two equations. Okay, so one is a dot by a the whole square plus some term related to the geometry, whether you use a flat geometry or a positively curved or a negatively curved space, and then how it is related to the constituents of the universe. And then there is another equation which is related to the acceleration of the universe. So you get these two equations based on the Einstein's field equations. And so you can combine these two to write something like this. So you get an acceleration equation for the scale factor itself. So it's not the first derivative, but the second derivative of this acceleration. And it is related to the density of the components in the universe and the pressure of these components. It looks something like this. So if you have normal matter that you know of, okay, it doesn't have any non-negative pressure, then you can see that this acceleration should always be negative. Okay? So in principle, you should be living in a decelerated universe or a decelerating universe, even though we see an expansion. And people have tried to observe this, and instead they find that, no, that's not the case. We find an accelerated expansion, okay, which means that some of the components should have a pressure which is very odd, right? And that's what we call dark energy nowadays. So where pressure is minus of the energy density that we see. So we'll not go again into the details of this, but you can start from this equation and you can work it out depending upon the different matter constituents of the universe or different constituents of the universe, what the scale factor as a function of time will look like. You take this equation, you figure out how rho changes as a function of the scale factor, and then solve it in order to get what A looks like as a function of time. This is a first order differential equation. dA by dt, right? So you integrate over time, you should be able to find out how A changes as a function of time. That was what was remaining, right? And so you can try to do this for different kinds of constituents. You can take ordinary matter, non-relativistic. And so the pressure, which is basically rho times V square, is much smaller than rho times C square because it is non-relativistic. And so P you can set to 0, close to 0. Right? And then if you take something like radiation, then it will have a radiation energy density, which is related to the pressure, which looks like this. So there is a 1/3 of rho that you get out. And so you take these equations, you can show that the matter density, it should go as a to the -3. And this is as expected, right? If you have ordinary matter and the volume of the box is growing, then its density should fall off as 1 over the volume. And so that's the reason why this rho matter is going as 1 over a cube. And the radiation, it goes as 1 over a to the 4, because not only is the volume increasing, but also the energy itself of these photons is falling. And so the energy density goes down as a to the -2. So once you have these equations, you can substitute them back here. Now you have basically everything is just a function of A and some constants. And so you can integrate to get what A looks like as a function of time. So again, in the exercises, I've given Python notebooks, which will be able to carry out these integrals so that you can write down and look at what A of t looks like. Okay. So please go through those things. Okay. So in general, if you have many different components, so here there is a matter component, a radiation component, something related to dark energy, for example, as well, and how it behaves, and then the curvature of the universe. Okay, so you have all these different components. You can write down what this first equation looks like. It looks something like this. Okay, and then you can try to integrate out this equation. Okay, to get what the scale factor will look like as a function of time. Again, since this is revision, I'm not going through details one by one of all of these terms, but there is a code which will tell you how to do this, and we'll go through it in the tutorial. Okay. And so the idea is simple. If you tell me what the constituents of the universe are today, and if I know how they evolve or how they were in the past, so that is what these terms are telling you, then I can tell you exactly how the scale factor varies as a function of redshift based on general relativity. Right? And so if I have this, I can compute A of t. If I know A of t, if you remember, I can compute the chi as a function of the redshift as well, right? Because I just have to do an integral of this. Right? Something which looks like this, right? And d chi. Sorry, what did I write? Sorry. Let me just do it properly. D chi is c dt over A of t, right? And so I can do these integrals as soon as I know A of t, right? Okay, and then once I know all of this, then it is very easy to also calculate distances in the universe. So that's what, again, in the tutorials, you try to work out what the luminosity distance of galaxies looks like as a function of the scale factor or as a function of the redshift of a galaxy, okay? Or how the angular diameter distance looks like. So all of these things then can be done through these equations that we have, okay? So let's stop here. Tomorrow, I will try to go through the cosmic microwave background quickly and how it can be used to get distances and the Hubble constant. And then I will show you the fact that there is a Hubble tension and how gravitational waves can address that. Okay? Okay. Thanks.
Thank you, Surhud, for kickstarting this course. Are there any further questions? Yeah.
Curiosity. So when you say that universe is isotropy, the proof is by CMB. Yeah. So I am asking that CMB is quite old, right? I mean, it could very well happen that there was some anisotropy, and now we have some anisotropy. It cancels out after the.
Yeah.
So I'm asking, is there a local or current observation, just like the galaxy structure we can see, for the isotropy?
Yeah, so in principle, you can do the same exercise with galaxies which are in this direction compared to that direction and compared to that direction.
So all
And
the
so-
radial direction.
Yeah. But you have to account for the fact that there will always be inhomogeneities. And these inhomogeneities will be enhanced by the time we see them now. But CMB is like quite far away, 380,000 years after the Big Bang. Today we are something like 14 billion years, right? And so it gives a snapshot which is way further out. And see, it's always comes down to Occam's razor, right? It will be so hard to take something which is so far away, have an inhomogeneity there, and then get it cancelled right where we are with some local thing. You know? So that's the reason why.
Sure.
Yeah.
Thank you.
You use the mic.
Yeah.
So how far away are the farthest of supernovae that we?
So farthest of supernovae that we have detected are beyond the redshift of 1 even.
So when we use those supernovae, are we actually measuring the Hubble's constant h naught, or are we actually measuring h as a function of redshift itself?
So what you measure is something called DL of Z. So the luminosity distance to these objects as a function of the redshifts of the galaxies in which they are staying. Then you build a forward model because of this, like with these equations, given the constituents of the universe, you can build out a model for what the luminosity distance will look like as a function of redshift. So again, like just to go slowly through it, you specify the constituents of the universe, you compute A of t. You can get what chi of A is by carrying out that integral, right? And then once you have chi of A, then you can calculate what the luminosity distance should look like as a function of scale factor or the redshift, because they are also synonymous, right? And so then you fit a model to it. You don't do it with the simple Hubble law. Yeah, that's not even done in the recital paper. So they will fit the full model.
Also, I've heard that the mechanism behind this type 1a supernova being standard cradles is something to do with the thermonuclear reaction triggering due to white dwarf accretion happening. So since we understand the physics behind this very well, should not we be able to calibrate it without
No,
resorting
so even the mechanism is not necessarily well understood. Like people think that it could be an accretion going on, but then how big was the star which was feeding into this supernova? What is the environment of this supernova? Plus, it could even be two white dwarfs going around each other and then generating this thermonuclear explosion. So I think there's a lot of debate about how exactly these type 1a supernovae even happen. So I agree that I mean Chandrasekhar mass limit that does give you some sort of a scale to anchor to, but still there are differences that you see and you observe directly.
Thanks.
That is hard to predict.
Okay, so let's break for coffee now and
You can
thanking
ask me.
Surhud once again.